Good morning, students. Today is our third lesson on geometrical optics. And today we will see total internal reflection. There is a L missing here, I'm sorry. So there is total internal reflection, and we will also see, if time allows, Fermat's principle. Do you know what is meant by total internal reflection? The name itself carries what is meant by total internal reflection. Reflecting completely. Usually, when light enters a transparent medium, we expect that all of the light passes through the transparent medium. We expect if light is coming from a room and going through the glass, we think that all of the light pass through the glass. But that's not true. Usually, a part of the light gets reflected back and a part get refracted. Suppose this is air and this is glass. Now, try this at home tonight. You have windows at home, right? Glass windows.
Sure.
Yes.
We learned the total of reflection is that a angle of incidence is greater than the critical angle.
Yes, yes. You have
This sum?
learned that. I'm going to
Yeah,
that. I'm going to it. Before that, I just want to clarify one concept. If the light is incident at any angle, a part of it will be reflected back to the same medium. A part is refracted. I want you to see that with your own eyes, where you can experience total internal reflection. That's why I'm telling you tonight, try this at home. At home, you will have a glass window, right? So switch on the light in your room. And when you go and stand about 1 or 2 meters away from the glass window and look straight through it, when you are looking straight through it, you are looking through the normal. Then you can see everything outside, lights, buildings, trees, what road, whatever it is, you will be able to see, or everything outside. Now slightly move sideways and look into the window, which means you are increasing the angle of incidence. When you move a little, you can see, like in this figure, here you can see a glass window. If a person is standing here, then sideways, if he looks, he can see both what is outside the window. See the trees here, ground here. Also, he can see the people walking through the corridor towards him. See a man with a white shirt. So if you are looking at an angle, that is, if the angle of incident is oblique, if the light is incident obliquely on the transparent surface, a part of it gets reflected. That is why this person can see other people walking through the corridor. Also, a part of light is refracted or transmitted. That is why he can see what is outside. So you can experience the same. When you stand at 2 or 3 meters and look at the window from an angle, you will be able to see both things outside and also reflection of things inside your own room. Now, try standing a little more sideways. Then you will reach a position where you cannot see what is outside. Even if you are looking through the glass window, you won't be able to see what is outside. Instead, you can see the reflection of all the things inside your room. Have you tried this yourself? Have you experienced total internal reflection yourself?
teacher never. No, we didn't
Okay.
realize waiting.
Yeah, you must have done that, but you didn't think in this direction. So try to do that tonight. At night, there are lights and also it will be more clear. Even in the daytime, it is possible to see. Okay, so let us see what are the conditions for total internal reflection to occur. Now, total internal reflection occurs whenever the angle of incidence is more than critical angle. critical angle, which is usually denoted by theta c or IC. So here you can see a picture where light is incident from a denser medium. Suppose this is glass of water and this is air. In most of the books, you can see refractive index represented by letter N, but in your textbook, it is mu. That is why here in this picture, it is N, but we learn refractive index as mu. It doesn't matter. In most books, it will be seen as N. And the angle of incidence here is theta 1. So if the angle of incidence is less than the critical angle, what happens? A part of light get reflected to the same medium with the same angle, because angle of incidence should be equal to angle of reflection. And a part of light will get refracted to the new medium. See, it's going to a rarer medium. That is why the refracted angle theta 2 is greater than the incident angle theta 1. Now, if you slightly increase the angle of incidence, if it becomes the critical angle, then what happens? The light, refracted light goes through the surface. As you can see here, the angle of refraction now is 90 degree. So the light ray after refraction goes through the surface of separation of the two media. There will be still a part of the light ray getting reflected back to the same media. Since the angle of reflection is equal to angle of incidence, both will be theta c, that is the critical angle. So let us see what is critical angle. When a ray of light of fixed color passes from rarer medium to denser medium. Okay, this is wrong. I will have to change this. What will be the condition? The light should travel from denser medium to rarer medium, right? Denser medium to rarer medium. Rarer medium, then the incident angle for which the angle of incident, angle of refraction is maximum. The maximum possible angle of refraction is 90 degree. That is, the refracted ray passes through the surface of separation is called the critical angle. So what is the condition for critical angle? It should pass from a denser medium to a rarer medium, as you can see here. And it is fixed for a fixed color. So for different colors, the critical angle also will be different. Okay, is that clear what is critical angle?
Yes, teacher.
Yeah. So that is the critical angle. Whenever light is traveling with the critical angle, it will go through the surface. The refracted ray will go through the surface. Now, what will happen if you further increase the angle of incidence? There will not be any refracted ray. All the light ray will get reflected back to the same medium. This is called total internal reflection. So what is total internal reflection? When a ray of light is incident from a denser to a rarer medium, as you can see here, with an angle of incidence greater than critical angle, then there will be no refraction. But the ray of light is totally reflected back to the first medium according to the laws of reflection, which means the angle of incidence will be equal to the angle of reflection. So can anyone, like Khadija, can you tell me what are the two conditions for total internal reflection?
The ray of light should pass from denser to rarer,
Yes,
and the incident angle should be smaller than the reflected angle.
it should be greater than the critical angle. The angle of incidence should be greater. See, this is the incident angle, right? Here you can see theta c is the critical angle. Angle of incidence is greater than the critical angle. Okay. In
Okay.
that case, all the light will be reflected back to the same medium. This is called total internal reflection. So suppose one of these medium, this is air, having refractive index 1. And suppose this is some medium having refractive index mu, say glass with refractive index mu, then theta c is equal to 1 by mu. This is the relation between critical angle and refractive index for a medium. We know that each color has got a different refractive index. So the critical angle also will be different for different colors. So the critical angle will vary according to the medium and also according to the color of the light. So theta c is sine theta z is equal to 1 by mu. I will just tell you how. We learned the generalized Snell's law, right? Mu into sine, angle in that medium, is equal to mu into sine, angle in the second medium. So here, suppose light is incident from here. Theta c is the angle in this medium and the refractive index is mu. So mu into sine theta c will be equal to refractive index of air is 1. Sine 90 is also 1. So on the other side, it will be 1 into 1. So mu theta c will be equal to 1 or theta c will be equal to 1 by mu. Is this equation clear to you?
Teacher, sine theta c, right?
Yes, sine theta c. Sine theta z is equal to 1 by mu. This comes directly from the Snell's law. And this equation is important when you solve problems. You will have to memorize this equation. Sine theta c is equal to 1 by mu and light is entering from a medium with refractive index mu at critical angle to air. Only then this equation will be valid. Okay. So the rarer medium should be air and the denser medium can be anything with a refractive index mu. Is this clear to you what is total internal reflection?
Yes, teacher.
Okay. So let us see a new concept called optical path before we go to the Fermat's law or Fermat's principle. Have you heard of optical path?
No.
Yeah. Optical path means the path or distance that the light would have traveled in vacuum if it is traveling in a medium. Where do light have maximum velocity?
Vacuum.
Vacuum,
What is the value?
3 into 10 raised to 8.
Meter per second. So light has maximum velocity when it travels through vacuum or air and it is 3 into 10 raised to 8 meter per second. Suppose light is traveling through glass. What about its velocity? Will it be more or less?
Less.
Let's
Less. Suppose light travels for 2 seconds through glass. Okay. How much distance it can travel through vacuum in 2 seconds? It can travel 2 times 3 into 10 raised to 8 meter per second. That is 6 into 10 raised to 8 meter per second. It can travel through vacuum. Can light travel for 6 into 10 raised to 8 meter per second meters in the glass in the same time?
no.
No, it will be traveling a lesser distance through the medium, right? So whenever you are dealing with the principles in geometrical optics, like when we are dealing with Fermat's principle, whenever light is traveling through a medium, you have to consider the optical path of the light, which means the length or distance traveled by the light should be the equivalent distance it would have traveled if it was in vacuum. That is called the optical path. So what is optical path? If light travels in a medium the equivalent distance the light would have traveled in vacuum in the same time is called the optical path. So whatever medium the light is traveling, it will have a lesser velocity in that medium. So the distance traveled by light in that medium will be smaller. But if with the same velocity, if light is traveling in vacuum, it would have it would have traveled a longer distance, right? That is called the optical path. Now, how can we find the optical path? That we are going to learn here. Suppose L is the distance traveled by light in time t in a medium of refractive index mu with velocity c. Then the time taken by light is equal to L by c, where L is the distance traveled and c is the velocity of light in that medium. Usually, in most of the books, we express the velocity of light in any medium as v and the velocity of light in vacuum as c. But in your textbook, the light velocity in any medium is expressed as c and the light velocity in vacuum is expressed as c naught. So I am making the same representation. That is why I have expressed the velocity of light in the medium with c. So suppose the medium have a refractive index mu, the time taken by light to travel a distance L will be L by c. Now, if the speed of light in vacuum is c naught, the distance that light would travel in vacuum will be L naught, right? What is distance travel? Velocity into time. So velocity is c naught and time, we know that we are considering in the same time as it traveled in the medium. So instead of t, I have substituted L by c. What is c naught by c?
The unit.
No, I'm asking
And
what is velocity of light in vacuum divided by velocity of light in the medium,
Refractive index of that medium.
Yeah.
active index of the medium. So C naught by C is equal to mu, refractive index. So we got the relationship between the optical path and the distance traveled by light in the medium. Optical path is equal to refractive index of the medium multiplied by distance traveled by light in that medium. Is that clear? So whenever we are using Fermat's principle and when light is traveling in a medium, we have to consider the optical path, not the actual path or not the actual distance traveled by light. We will always consider the optical path. We will get it by multiplying the refractive index of the medium with the distance traveled by light in that medium. So this you have to remember. What is optical path? Bibi, can you tell me what is optical path? Define optical path.
If light travels in the medium, the equivalent distance that light would have traveled in vacuum in the same time is called optical.
It is called the optical path. South, can you tell me the equation to find optical path?
refractive index of the medium multiplied by distance traveled by the light in that.
In that medium. Okay. So you will be usually given the distance traveled by light in a particular medium. But whenever you are using the laws of geometrical optics, you have to consider the optical path. Okay. Now let us see what is Fermat's principle. Now Fermat is the name of a scientist. This will be new to you. In 1650, see how old it is. In 1650, geometrical optics is old. Fermat discovered a way to explain reflection and refraction as the consequence of one single principle. It is called the principle of least time or Fermat's principle. In fact, Fermat gave two principles. One is called the principle of least time, and the another one is called the principle of least distance or extremum path. Let us see what is Fermat's principle. Fermat's principle of least time states that light travels between 2 points along the path that requires the least time as compared to other nearby paths. What does that mean? Whenever light is traveling between 2 points, suppose light is traveling from here to here, then it will take that path for which it will reach in the least time. What is the path taken if it is traveling in the least time?
Optical.
The distance between these two, a straight line, right? Will the light travel like this and reach here? No. Will
No.
the light travel all this way and reach here? No. Light will always travel in the straight path. What do you call that? It's an important property of light, that light in a homogeneous medium has, what do you call that? We know that from our experience, but there is a name given to that particular property of light. Light traveling in a straight line. What is it called?
Wave.
Rectilinear propagation of light. That is called rectilinear propagation of light. When we started geometrical optics, we told there are few major assumptions. One is that light makes rectilinear propagation. That means when you use a torchlight, have you ever used torchlight?
Yes, teacher, we use.
Yeah, I don't expect you to use, because in my generation, of course, we use torchlight, because there will be load shedding, current will not be there in the evening for some time. Or sometimes we will have to walk through paths which does not have street lights. So we use torchlight. And if you use torchlight, you can see that round part straight on the ground if you put it to the ground, right? Why is it so?
So what did you say?
If you put a torch light onto the ground, you can see that round color on the ground. Why?
Brown color.
Round, round,
Oh, sorry, round. Okay.
Because of
round.
the shape.
Yeah, the shape.
Because it's
Because,
perpendicularly, right?
but because the light is traveling in a straight
So
line. Now you will think, why the surrounding area become faintly visible? Why? If the light is traveling in a straight path only, if you are using a torch light, you should be able to see only one straight path, right? You can't see anything in the surrounding, but it will be visible a little bit. Why?
Because diverges. The ray of light diverges, right, to the whole area.
Light diverges only if it is traveling from one medium to another medium. It's air surrounding it. It's because some of the light rays get scattered by the air molecules surrounding. That is why we can see a little bit visible in the surrounding area, but most of the light will travel on straight. So if you are in space and
Teacher?
yes, yes,
No, I was going to ask in what if there is the vacuum?
yeah, if it was
I was
in
going to ask.
vacuum, will you be able to see the surrounding? No,
No.
it will travel straight. See, sun is far away from us, right? Sun is far away from us. Still, sun's rays reach Earth's surface. How? Why is it reaching Earth's surface all the way?
Because nothing is there to oppose it.
Nothing is there to scatter the light. Only
Okay.
light gets started scattering once it enters the atmosphere. Okay, before that, all in that vacuum region, light is traveling in a straight path. See, this is said by Fermat's principle. See, with one principle, Fermat can explain rectilinear propagation of light. We know that whenever there is a straight path connecting two points, that will be the path that light can travel in least time. So light travels between two points along the path that requires the least time as compared to nearby paths. So this is Fermat's principle, and this clearly explains rectilinear propagation of light. So in vacuum, light would travel in a straight line. Now let us see Fermat's principle of extremum path. Extremum means it can be least or minimum or maximum. If light is getting reflected from a plane surface, then according to Fermat's principle, the light travels in a path that requires the path which is least. But light can be reflected from curved surfaces as well. It can get reflected from convex mirrors and concave mirrors as well. So whatever be the mirror, this extremum path principle stands. Fermat's principle of extremum path states that light travels between two points along the path whose distance will be either minimum or maximum. What is meant by will be minimum or maximum? It will be either least or the maximum. How can you mathematically show a quantity is minimum or maximum or a constant? How can you show with calculus that some quantity is a constant or a minimum or a maximum?
Integration and differentiation.
Differentiation.
Sorry.
Difference means change,
Limit.
right? So difference or change is zero, then it will be a constant. For example, a body is traveling with uniform speed or uniform velocity. What will be dv by dt? Rate of change of velocity with time.
0.
Zero,
Constant.
because velocity is a constant, and acceleration therefore will be equal to zero. It is rate of change of velocity. Now suppose an object is at rest, then what will be its dv by dt? Sorry, dx by dt.
0.
Zero. Rate of change of position with time is zero. So mathematically we can show by Fermat's principle, the light travels uh, between two points along the path that requires the least time by showing dl by dt is equal to 0. Because the length will not change with time. It is taking the least time. Sorry, dt by dx is equal to 0. dt by dx is equal to 0 means it is taking a constant time to travel that distance. With the distance between the 2 points, the time taken will not change. Okay, so you have to show dt by dx is equal to 0. Or you can also show Fermat's principle of extremum path by showing that dl by dx is equal to 0. Suppose there are two
Teacher,
points. Yes.
so can you repeat that part dt by dx? I didn't understand that part.
Suppose there are 2 points separated by a distance x. Okay. Then dt by dx is equal to 0 means the time will not change with respect to x.
Then what does dx by dt mean?
Dx by dt means as the time changes, the distance will not change.
Even if it's equal to dx, dx by dt equal to 0, that also means that
The
time will not
position
change.
of the object that will not
Will
change.
not change
Yeah,
with the change
position
of
of
time.
the object is not changing with time. Right?
Okay.
The other way, the time is not changing with the position.
Position. Same only, right? Just opposite.
Yeah. Means or the time is least or constant. Suppose you have 2 points, then the time taken by the particle to move from one point to another is least or constant, means dx by dt is equal to 0. Because what is constant here? Time is constant. When you consider an object who is at rest, its position is constant. That is why dx by dt is 0. Here, the time is least or time is constant. That is why dt by dx is equal to 0.
Yes, teacher,
Here,
got it.
Fermat's principle of extreme path states that light travels between 2 points along the path whose distance will be either minimum or maximum. So here the distance or the distance traveled by light should be constant. So you will show that mathematically by dx by, dl by dx is equal to 0, where L is the distance traveled. Now we will do that mathematically tomorrow because there is no time. And tomorrow we will use Fermat's principle to prove the law of reflection, that is angle of incidence is equal to angle of reflection. And also we will use Fermat's principle to prove that the Snell's law of refraction, mu sine I is equal to mu sine r. So we will prove both both laws of reflection and refraction using Fermat's principle tomorrow. So is that clear what is Fermat's principle?
Teacher, I have a question.
Yes.
If dl is the distance, then what is dx?
Dx is the distance between the 2 points which we are considering.
Then dl is the
dl
distance.
is the length traveled by light. See, if there are 2 points, suppose here and here, the distance between these 2 points is x.
Okay.
Now, light can travel from one point to another, either by traveling from here to here to here, or straight.
Okay.
So, light will follow from that part to that part only in the least or maximum distance possible. I will
So
show
now,
that tomorrow when we draw the figure and show it in reflection. The difference is that here we are considering rectilinear. Now think of reflection.
so normally dl by dx will be equal to 1, right? Because both of them
No. In
will
the
be.
case of reflection, it won't be. Suppose this is a mirror. Here, after reflection, light is traveling, coming here and going back to here. What is the 2 points? This and this.
Okay,
So
okay, it will
this is
be
the
greater, yeah.
distance between these 2 points. While the distance traveled by light will be here to
More.
here. Reflection. Got it?
Yes. Only in case of reflection, right?
Reflection. Yeah.
But
Also,
normally dl by dx will
refraction.
be 1.
Refraction. Suppose
Okay,
there are 2
refraction. That's
points here.
another one.
A fish and our eyes. We are looking at the fish in the water. Will light travel in a straight line? No, light will bend, right?
Yes.